Soon, so can you please, wherever you're talking, please come back to here. Thank you very much. Hello, we're going to start soon. Thank you. Sorry to interrupt. All right, thank you.
Good morning. Last morning presentation of the conference. It's an honor. I'm Wouter. I'm a postdoc at Inria, Rennes in France, and I'm going to present some work I did with Julien and Pettre. The title might sound a bit mathematical and scary, but rest assured there will be no math at all in this presentation, so hopefully that's a motivation to keep listening and watching until the end. Plus it has characters doing strange things, so it's always fun. Alright, so to give you some motivation, I do research on crowd simulation, which is creating computer models that can simulate mostly the navigation behavior of humanoid characters in a virtual environment. And preferably we want to simulate many people at the same time, in real time, so that we can use it for games or other interactive applications. So this is what the result, or a screenshot of the result of a crowd simulation could look like, and each person has its own wishes, its own behavior that we are trying to model, and they should not bump into each other and so on. So there's a category of simulation algorithms that is called agent-based, and there you model each person in the crowd as an individual agent with its own properties, its own personal goals, and possibly also its own algorithms for getting where it wants to be. So this is what a typical crowd simulation looks like. This is the kind of stuff I look at all day. And so forget everything you've learned in this week. People are disks, just so you know. And so every disk you see here is obviously a top view from a crowd, and every disk is a person who wants to get to the other side of this corridor while avoiding obstacles, but also each other. And there's no global control over who has to do what. They all have individual choices that they make. So I'm particularly interested in navigation in environments that have obstacles in them, so where it's not just one corridor with just people, but also geometry that people have to avoid. And then the problem gets a bit more complicated, and people typically split it into multiple parts. And so there are actually different levels of navigation going on. And on the top there's what we call global planning or path planning. This means given an environment with some obstacles, use some data structures and algorithms to compute a curve that would send an agent from start to goal. And this is then the overall plan that the agent it will try to follow while avoiding other people. So that's the first phase, the highest level. And this part ignores the presence of other agents largely, so it's purely based on the geometry of the environment. And then the simulation loop kicks in, so it's a process that repeats itself over and over again. And this consists of at least two steps. The first is path following, where the agent computes a way to get further along its path, but still ignoring other agents. And after that is collision avoidance, where the agent takes his preferred velocity as input and changes it a little bit so as to avoid other people that are moving around. So this could be changing the angle, but also changing the speed, or maybe a combination of both. So this combination works, except when it doesn't. So there's a problem. The assumption is that every level solves a part of the problem, and therefore they solve the whole problem together. But there are actually cases where these different levels kind of disagree on what they want the agent to do, and then you get strange behavior. And once you know how it works, it's pretty easy to trigger this sort of stuff. So here's an example where I send an agent from left to right through a passage that has some agents in it. And if you play it, you get this. And I hope we can all agree that this is strange. And so what's happening here is that the path following will always try to let the agent follow this initial path that they had in mind. Whereas the collision avoidance, it clearly sees that this is not possible, so it will steer the agent away a bit. But at some point, the path following will take over and say, no, this was not your plan, go back. And then there's this conflict that doesn't end. So obviously the solution here would be to take a detour in either direction, so to actually change your global plan based on something that's happening on a local scale. So these levels have to communicate. And this is easy for us to see, especially from above. We can, as humans, easily see what's supposed to happen. But these kinds of problems are actually pretty hard to detect and to solve in a systematic way. So that is the motivation of this paper. The goal is to solve navigation problems that are caused by these conflicts between local and global planning. So the underlying thought is that currently, or so far, these levels had no common way to express what they wanted the agent to do. Like one made a path, and the other makes a velocity, and it changes every step. But yeah, we just combine them and hope for the best, without any communication between them. So in this paper, we then collaborate via a topology-inspired concept. And very roughly speaking, we define a navigation strategy as a combination of intentions to pass obstacles and other agents on either the left or the right, which induces a sort of a coloring of the obstacles and the agents. And then, if we can do this for all these levels, we can compare them and check for conflicts between them, and if there is a conflict, we can systematically describe how to solve it, or what the agent's options are to maybe solve it. So yeah, here's the main idea. If an agent is following or has a path in mind that it wants to follow, but then at some point there's something going on locally that prevents the agent from doing that, we can detect the conflict because we wanted to pass this obstacle on the left first, but collision avoidance says maybe you should consider doing it on the right. And at this moment we can detect this conflict and suggest a detour that actually follows the local advice from the collision avoidance. I hope that makes sort of sense. But you will see more examples of this. So if I had to summarize related work in one sentence, which is very scientific, I would say that everyone else has been trying to add more algorithms to this loop, so add more things between global and local, so as to make the gap smaller, but actually you make multiple gaps that are small. And you still combine things without any communication between them. You still hope for the best. So compared to that, we don't add new algorithms, but we synchronize existing ones by thinking about what they are actually trying to do in a way that makes sense. So that was our overall introduction. I'll go quickly into some of the details. I see I didn't reset my timer, so I have no idea where we are in terms of time. So you can define a decision with respect to a single object as either you want to pass it along the left, which I color in red, or you pass it along the right, which I use blue, or there's a third option where you haven't made a decision yet, for example, because the obstacle is far away, like falling off the slide. That's the third So a strategy is then a coloring of all obstacles and all agents into red, blue, and gray elements. Or a partial red-blue coloring where gray is just everything else. Now I will leave out the details of how we do this, but the paper shows that you can obtain such a strategy from a path. So if you have a curve that goes through the environment, passing obstacles, you can quite easily compute the colors of obstacles that belong to this, but also for velocity. So again, this is only on the obstacle level, we don't look at other agents yet, but on the local scale, like this is a velocity that the system says the agent should take in the next few time steps. And from that we can calculate what this means in terms of navigation decisions or passing directions for each agent, but also for each segment of nearby obstacles. So as you can see, there are now two ways to obtain colorings, and there can be differences between them. So we can say that there is a conflict if one strategy colors an object red and the other colors it blue. And now that we have this system, we can start truly comparing these navigation algorithms and checking systematically when they don't agree with each other. So to go back to the framework, these are the same three steps again. There's global path planning, where you compute an overall curve. And then there's a simulation loop that is repeated over and over again, where you first compute a preferred velocity that lets you follow the path, and then you compute a sort of new velocity or final velocity that also avoids other people that are walking around. Now we propose to add a third thing to this, which we call the strategic level, and there we convert these two velocities to a strategy, so to coloring, and we check if they have a conflict related to obstacles. So if path following colors an obstacle red and path collision avoidance colors it blue, or the other way around. And that's exactly the same example again. So the preferred velocity would send you all on one side, but the new one would send you along the other, so you get two different colors. Now if this happens, you could give the agent at least three options. You could let them take a detour, like an alternative global path that satisfies this difference that we found. So that's the same picture as before. Or you can use a alternative velocity that deliberately follows the plan you had in mind, so it kind of overrules collision avoidance in this case. Or you can just use the velocity that is currently suggested and not worry about it. That's basically what we've been doing all the time. So it kind of ignores the strategy concept. So those are the three options that you have. And there are many ways to choose between these. I think it's kind of a side thing, not the most important aspect. So we suggest one way to choose in the paper, but you can look at the paper for details. So that is the method. And how much time do I still have? Sorry? 6 minutes. Ah, that's nice. Okay. So I will show just a few examples. Here's a simple demo scenario where one agent has to go from left to right, while if you do global path planning, you get this curve in our case. And as you can see, it goes through a couple of areas that are kind of problematic and that you want to avoid by the local observations that you make. So if you don't do anything special, the agent will get stuck at the first opening that is blocked by other people. So this is the same situation as in the beginning, but with more other things going on around it. But if you use the strategic level with the right parameters that I conveniently left out here, you will see that the agent, on a couple of occasions, it changes its global plan and it avoids all the problems. So here it goes down eventually because that crowd flow is easier to pass. And then here at the end there's another blockage that it avoids. So that's for a single agent. And you can apply this to many agents at the same time to get a different flow of the overall crowd. So here I'm going to send lots of people from the top left to the bottom left. Again, if you don't do anything special, they all try to take the shortest path and they get stuck at certain places. Like the biggest problem is over here. And there are clearly alternatives that they are not using because they just don't realize that this option is there. But if you add the strategic level, then you will see a much more dispersed crowd flow where people take alternative paths based on local situations that they encounter. So it's already much better, I think. There's some agents who do encounter weird things, but overall the crowd flow is much better. You can calculate that many more people reach their goal in a certain amount of time. So there's actually a bonus application that I call environmental guidance. You can use this strategy concept not only to look for conflicts, but also to force agents to make certain decisions. And this sounds really easy, and I guess it kind of is, but it's like a bonus thing that you can also do with the definitions we had. So I'm going to do a bidirectional flow, so I will also have people going in the other way. And without any additional measures, you get like a mosh pit in the middle where bad stuff happens. But what you could do is give a few obstacles a color and tell people that their global plan has to pass these obstacles along the right, for example. And then you get a nicely regulated crowd flow, and this is kind of comparable to having a directional sign on these pillars, but with an arrow pointing to the right and forcing people to pass it on a certain side. And of course you can combine this with people who ignore the sign, for example. So yeah, that's all the examples. So just to give some conclusions and some outlook for future work. This method shows that the concept of a navigation strategy can help navigation behavior for agents in the crowd. So what we've done is we've added a topological meaning to all the navigation steps that were already there. So we didn't add new algorithms, but we just thought about what they were actually trying to do. And this coloring concept, it helps you detect and resolve conflicts between algorithms and kind of bridge a conceptual gap that has always existed between them. So what I've left out is that it's easy to integrate. It's just an extra step that you have to implement, and the details of the other methods really don't matter. And in the paper we also show that with the right settings you can maintain the real-time performance of the system. So you can simulate, at least on my laptop, thousands of agents in real time, just by controlling that they only replan global paths when they really have to, because this global replanning is the most expensive step. But if you are a bit more critical, of course, this doesn't solve every navigation problem that's out there. So it still relies on the individual algorithms being reasonably smart. So if your collision avoidance algorithm is very stubborn and it will never even suggest a detour, then it will also not be detected by this overall system. Also, if you go into a passage and you then encounter a problem, the method currently doesn't allow you to turn around and do a 180 and do something else entirely. So there are some limitations there. And yeah, to kind of relate it, it's a very complex system. Crowd simulation has always been super complex, so it depends on a lot of algorithms and also on a lot of settings within the algorithms. The good thing is that we haven't added a lot of parameters on top of it, but it still depends on the details. So for future work, I would like to add more levels. Like there's something called midterm planning, which is slightly smarter than collision avoidance, and so it lies between global and local. And I think if we add this in between, you can also get conflicts at different levels, also conflicts related to agents and not just to obstacles. And I have the feeling that eventually this strategy concept could be the thing that glues it all together, that gives you a more abstract understanding of what's actually going on. Another thing, this picture is just to mess with the English. We can use this guidance concept, so this coloring of obstacles, to kind of mimic how people would respond to signage in the real world. And finally, on the very, very long term, I think this might lead to some simulation methods where it actually doesn't matter anymore what you call global and what you call local. I hope that eventually we will end up with some system that can do everything, where you don't have to decide whether something is a global obstacle or not. It's just one holistic thing, maybe based on the strategy stuff that can solve it. So that's it. This QR code will lead you to the video that shows all of this again without my voice, so that might be interesting. And thanks, I'll take some questions now.
Okay. So, who wants to?
Yes, have you thought about integrating cultural rules? Like, we are here in Britain, so this is left-handed traffic, and I constantly bump into people because I try to avoid them on the wrong direction.
Yeah, I do the same. It's possible right now. I kind of leave it to the user or the designer of the simulation. At least what I wanted to show is that the system allows it. So I think it's relatively intuitive to just assign a color to an obstacle, and then it has this meaning that you can kind of reason about. But you can do the same thing with keeping on the left or right hand side of the road, for example. And this would actually be a step in your global planner, where if you have a wide corridor, this blue curve that you try to follow is not through the middle but through the right, for example. So it works a bit on a different level maybe, but yeah, I think it would work. Yeah.
So right now you have established this empirical modeling based approach to open new windows and more options for navigation. So I wonder, do you in general think that a data-driven thing would be brought in at some point and where?
I was counting on this question, but my answer changes a little bit every hour. I think the data-driven stuff, personally, I think we should not go for that until we are sure that something is too complicated to capture with rules. Like if we do it too soon, maybe we don't get the insights we want. But I think it can be good for like reproducing certain types of behavior that is observed. So if you have a recording of a crowd, you can maybe use deep learning techniques to create a simulated crowd that sort of behaves the same, where you don't have to specify what the same actually means. Because I think that is the main problem, that we don't really know what similarity is between two fragments of crowd motion. So in that area, I think deep learning could help, because I think we have to accept that we will never understand this in a rule-based way. So for there, yes. But I think then, in the end, once you have this style that you want to reproduce, you still have to translate it to a system like this one, where you can actually give people individual plans. But yeah, I think it could be somewhere in between. Anything else?
In the model as you have it, you're doing this very discrete sort of left-right decisioning. Did you consider or already consider sort of more continuous values? So just to give an example, if I'm walking down the sidewalk and there's a crowd, I might step into traffic, onto the street a little bit, but I'm not going to step too far into the street, because it then starts to become dangerous. And so if I have to take too many steps in that direction, I might choose to go the other way. So is that something you looked at?
Yeah, so then you would have, what I showed here was just an environment that has hard obstacles and free space and nothing in between. So you would then end up with like maybe weighted regions where you have preferences for certain things. We've done stuff with that. You can show that the whole problem gets a lot more complicated, of course. But I can imagine that the choice for certain terrain types, it can be part of this topology description. It could be.
So, thanks for the interesting presentation. So, have you thought of comparing this against continuum crowds or methods that include potential fits to guide the agents around?
I didn't. I would like to implement one at some point, just to have done it at least once, because they're really interesting techniques. And usually in our introduction sections we say there's agent-based and flow-based, like continuum crowds. And the flow-based ones they're good at dense crowds, for example, but less suitable for people who have individual properties, like every person cannot have its own role, maybe different fields for everyone. So I think they have different applications. Like you have to decide in the beginning what kind of thing you're going for and then choose one of the two. But I think that's maybe if on the long term, if we want to go for some method that does everything, we need to look at this flow-based, these ideas, and maybe cherry pick some of that or combine it with some method. So I didn't do comparisons for this, but I think we will need to use some of the concepts from it at some point.
Okay, so I think we're in bit of time. I have a lot of questions to come later, but I think we need to move on to the next presentation.
All right.
Okay?
Thanks.